Good evening, everyone. Thank you for joining us. This is Brene Lloyd from Northwatch, and this is the fourth in our February 2022 Nuclear Waste Online series. And I'm really pleased to have co-panelists Dr. Ola Hendrickson and Bill Knoll here with me this evening, and Kathleen Brosmer is our chat master. So this evening, we're going to be looking at repackaging of radioactive waste, and more specifically, we're going to be looking at the used fuel packaging and transfer stages for the Nuclear Waste Management Organization's proposed deep geological repository. So we're going to go first some background and context, which we do every session. Then we're going to look at very briefly used fuel transfer stages. And then we're going to look in more detail at the Nuclear Waste Management Organization's used fuel packaging plant. And then for comparison's sake and insight from other jurisdictions, other experiences, we're going to look at the Swedish proposal by SKB for a deep geological repository. We're going to look at Yucca Mountain, a US now stalled, hopefully permanently, proposal for a deep geological repository in the state of Nevada. Look at hot cell experience at Chalk River with Ole, and then a brief summary, and then we'll go to Q&A. So I'm going to change my view. So background and context. So we do this series every February. And as a sharing and information sharing and learning experience related to primarily the Nuclear Waste Management Organization's proposal to bury nuclear waste at some location they are still in search of. To date, the industry in Canada has produced 3 million bundles of nuclear fuel waste, 60,000 tons. And since 1977, they've been developing plans, various plans, to bury the waste in various locations. It started in the 70s with a brief report, 3 men, 3 months, looking at the problem of nuclear waste, decided it should be buried. In the Canadian Shield at that time, a failed site search, a failed geological disposal concept development by Atomic Energy of Canada Limited. And then in 2002, the Nuclear Fuel Waste Act was passed, giving a green light for the nuclear industry, the nuclear power companies, utilities in Canada to organize themselves as the Nuclear Waste Management Organization. And they did a study process for 3 years, and in 2005 introduced adaptive phase management, their version of a deep geological repository. High-level radioactive waste has not been buried anywhere in the world. Despite more than 40 years of effort by the nuclear industry. At this point, 10 years into their site search, their site pursuit, the Nuclear Waste Management Organization has now focused in on 2 different areas: South Bruce, near the hamlet of Teeswater in South Bruce in southwestern Ontario, and an area, the Revel Lake area between Ignis and Dryden in northwestern Ontario. Nuclear fuel waste, the issue is that the fuel waste are highly radioactive and they will remain hazardous for hundreds of thousands of years. And I want to note, particularly for this evening's presentation, that even low levels of radioactivity can cause health problems. This was affirmed in the BEER 7 report and their conclusion that there is every level of exposure to radiation produces a corresponding increase in cancer risk, but it's not just cancer risk, it's other health effects as well, largely related to the immune system. We're going to look at the used fuel transfer stages. So the fuel goes into the reactor as uranium. It comes out of the reactor after 18 months and is transferred to the irradiated fuel bay, the pool at the reactor station. After 6 to 10 years in the irradiated fuel bay, it's transferred to dry storage at the reactor station. 6 to 10 years is the general term that industry describes. In fact, a large amount of the fuel is staying in the irradiated fuel pool for much longer than that prescribed time. And then the final transfer at the reactor station is to a used fuel transportation container. The NWMO has for years, in recent years, been talking about the used fuel transportation package, which they described as certified, has gone through, well, they reference safety testing, implying that the used fuel transportation package has gone through those tests. But more recently, they've introduced in September 2021, they introduced the basket container, which will be for any waste other than Ontario power generation waste. And there is a third container, which they had discussed in earlier years, a dry storage container, which they have to some degree reintroduced. But generally, they speak now of two different containers. But they do not at any point describe dry storage, that transfer from the dry storage to the transportation container. That's just a blank in the NWMO description of their project, of their process. But they do in a transportation system conceptual design report from September 2021, they do state that the waste owners are responsible for the retrieval of the used fuel from storage, preparing and loading the transportation package with used fuel, loading and securing the transportation package. So NWMO describes it as a gate-to-gate transportation. It's an interesting separation they're attempting to establish here, because in fact, the Nuclear Waste Management Organization, they are the waste owners. They are Ontario Power Generation, Hydro-Quebec, and New Brunswick Power. So in my view, it's a false distinction. But we have not been able to find in any of the NWMO documents any description of that transfer. Some of that waste has been in dry storage containers for decades. There's no description of how that transfer is expected to take place. And it's something for those of you who are living in reactor communities, it's an issue that you may want to raise sooner rather than later. So we're going to look at the NWMO's used fuel packaging plant concept. So this is the plant. It's part of the NWMO's surface facilities. You'll see their larger set of surface facilities, and included in that is the used fuel packaging plant. So you see in the lower part of your screen, that's the used fuel packaging plant. The black arrow points to how it's located within the broader property of the surface, what the NWMO describes, the surface facilities at their proposed or hypothetical conceptual deep geological repository site. So for this used fuel packaging plant overview, and this is an overview, it's a general description. It's not a technical review. We have not yet undertaken that. These are the documents that we relied on for this, to prepare this overview. So we looked at the 2017 and 2018, what they're called reference cases, titled Post-Closure Safety Assessment, one for crystalline rock in 2017, sedimentary in 2018. We looked even more closely at the September 2021 Deep Geological Repository Conceptual Design Report. And then we looked at two different presentations NWMO staff has made to community liaison committees in South Bruce, both in South Bruce. So the 2018 document, 2017 and 2018 documents are quite similar. And but they describe there are some fundamental differences between those reports in 2017, 2018, and the 2021 report, which we're going to rely on most heavily for this review. One fundamental difference is that in 2017, 2018, it was a one-story building, a two-story building. The fuel would enter through a basement and be brought up to the ground level. they did include a description of hot cells, not a detailed, extensive description, but there was a description of the hot cell areas. The 2021, the September 2021 report describes the used fuel packaging plant as a single story structure, and they have very, very limited references to hot cells. They refer to them as shielded enclosures. There's a couple of different passing references, but there's very little actual description of the hot cells, and we will look at what they do include. It's not surprising, I suppose, that there are these fundamental differences between the 2018 and the 2021 report. The NWMO does describe their project as being adaptive. It's very adaptive. And Hannah Guo, who is the NWMO lead for the used fuel packaging plant, did present in August of last year to the South Bruce Community Liaison Committee. And she described that she's part of a newly assembled team, but she emphasized that the used fuel packaging plant is conceptual. It's a concept. They're working on a conceptual design of the plant. She referred to the concept they have today is to utilize hot cells for our main processes. And they're in the conceptual design phase. And she said at that time in August that they were undergoing an option evaluation study as we speak. So I found that surprising in August 2021, almost 20 years after the NWMO was established, more than 10 years after they have launched their siting process, and they described their process as a package, and as a package which is known. And I find this is a very good indicator of how unknown the NWMO package or project is. It's very much a concept, and the used fuel packaging plant illustrates that. So the used fuel packaging plant, it's challenging to get a very detailed picture of the packaging plant graphically because there have been changes. You can't rely on the 2017, 2018 documents, even the 2020 documents that Derek Wilson used to present to the South Bruce CLC shows a different configuration than we see in the 2021 report. They describe the graphics portray different aspects. So a little challenging, but we've tried to, pull it together for an easy walkthrough of this facility. So the first location, of course, is where the fuel is received. Just walking through these steps, then it's removed from the modules, modules within the used fuel transportation package. It will be removed in a different location here if it comes in basket, here and here if it comes in the used fuel transportation package. They'll join up here. Then it's transferred into the used fuel container. Then the cap is welded on the used fuel container. Then the weld is inspected. Then the used fuel container is decontaminated. Copper is applied, sprayed on to that weld. It's a very thin copper. It's 3 millimeters of copper over a steel container. And at the weld, they will do a cold spray application at the used fuel packaging plant. And then that will be smoothed. Then heat will be applied to soften that copper application. Then the used fuel container will be placed in the buffer box, and it will be dispatched to the main shaft. So the description, very, very limited description of this pretty major step, this transfer of the used fuel container to the deep geological repository. It says the buffer box transfer cask with UFC will travel through a dedicated travel to the main shaft. That's the description. And it will travel in a tow vehicle and trolley. Very, very limited description or discussion of that important stage. So there is some discussion of hot cells in the used fuel packaging plant in this concept report from 2021. They're mostly references. So they refer to the solid waste that will be generated. It defines a hot cell. It refers to the hot cell equipment generating solid waste. It identifies hot cell vacuum filters as being part of the solid waste, although it never actually identifies that there will be filters to the air filtration system used in the air filtration system in the used fuel packaging plant and in the hot cells, something that you would think would be standard and that we could assume, but you'll see later in the presentation why there is perhaps reason to question that. And then it identifies that zone 4 area will be for hot cells. Then this is the entirety of the description of the hot cells in zone 4. So it does identify that there will be high radiation fields, there will be unshielded used fuel sources. That means there will be the fuel waste bundles without shielding, without separation between those highly radioactive sources and what surrounds it, the environment that surrounds it. The hot cells are used. They have a negative pressure, so the idea is that they will keep that contamination within the hot cell through this negative pressure. It says there will be monitoring and monitoring instrumentation, but it doesn't describe it in detail. It acknowledges there will be doses of radiation and that there will be monitoring of personnel for that. But it's limited, and I'll show you later where there are some internal conflicts in the document. One of those internal conflicts is around who is actually going to be monitored with a dosimetry device, and then it describes very generally some of those whole body monitors or dosimetry monitors that could be used. That's pretty much it for the description of hot cells in this report. So there's nothing detailed. There's no estimate or information about radiation releases. Aside from acknowledging that there will be monitoring, there's not really any discussion of the need for monitoring. Maybe it's obvious because these are highly radioactive. They will have that radioactive field. They will be, a source of, fairly high dose. There's no discussion of how that dose will be estimated. And it says in one location that the dose monitoring is limited to personnel who have a reasonable probability of receiving a recordable effective dose greater than 5 millisieverts, which is a significant dose. And it has a statement that all the shielded cells will be environmentally controlled by an active ventilation system, but there's no confirmation of filters in that ventilation system. So there was some discussion by Hannah Guo when she presented to the South Bruce CLC of hot cells, and she provided a very general description of a hot cell, but again, not really emphasizing that the reason for the hot cell, why is it a controlled space? Well, it's a controlled space because there will be an unsealed source. There will be exposure to a highly radioactive source in that hot cell. And she describes very generally activities that will take place in that in those hot cells. She describes some safety measures, but again, there's no actual description of what the monitoring will be, what the estimated doses are. There's nothing quantified in any of these descriptions. And then she describes that there are two options the NWMO is considering, stainless steel or concrete, and noted the price differential between those two different options, with the stainless steel being more expensive. There are a number of internal conflicts in this report that I just want to touch on briefly. This isn't a complete list, but I think this is a set of examples that I think indicate the kind of difficulties that you will have when you review this document. You'll flag when you review this document. So the first conflict point is that radiological calculations have been carried out in selected aspects of the DGR design element to confirm that the potential whole body dose during normal operations will be below limit. That's in the summary. That's right up front in the executive summary. It bodes well. It suggests that there's actually going to be detailed discussion of those calculations found in the report. Those radiological calculations are not presented in the body of report. There's a sole reference to external dose rate on transfer casks. That is the limit of what I was able to identify in terms of what could be called radiological calculations. There is in two different parts in the report, there are statements that say all fuel bundles are a minimum of 10 years out of the reactor prior to shipment. That was surprising because by my best recollection, all previous references have been that there will be a storage time of 30 years from discharge, which is the conflict point with this statement. But at a different location in the report, there was a similar statement about 10 years out of reactor prior to shipment, and the context was that towards the end of reactor lifetime or end of reactor decommissioning, the waste could be shipped as early as 10 years after discharge from the reactor core, which is really quite an extraordinary departure from the earlier statements that it would be 30 years from discharge before the fuel would be moved. The use of remote handling techniques will be considered is one of the statements early in the report. And then the report goes on, and I provided only a few examples, provides several examples of where remote handling techniques are going to be used in the process. So the question is, are those remote handling techniques that are described in later sections of the report, are they part of the plan, or are they techniques that are going to be considered? It's difficult to imagine that this kind of operation could take place without using remote handling techniques. But the statement at the beginning of the report that they will be considered really sort of puts later statements to question. And then we come back to this statement about dosimetry. So on one page, page 141, earlier in the page, it says a licensed dosimetry service will be used to measure radiation dose to all employees who have a reasonable probability of receiving a recordable effective dose due to work at the facility. It raises the question of, whose determination of reasonable probability. That doesn't sound precautionary. It raises that question, but later in the same page, it goes on to state a reasonable probability of receiving a dose greater than 5 millisieverts in a 1-year dosimetry period, which is quite a significant dose. So just a quick look at other surface facilities at the site of the geological repository. This isn't, again, a complete list, but I flagged a few that I think bear more attention. in most cases. So waste rock pile, this is going to be a very large footprint on the site. There's also no recognition of the acid mine drainage potential that could be associated with this excavated rock pile, storage area, I think they call it. An interesting contrast I find when they describe the construction camp, they get down to the level of detail of saying which class of employees will have their own bathroom and which class of employees will share a bedroom and possibly also a bathroom. An interesting level of detail for the construction camp compared to the real lack of detail in so much of the report overall. The protected zones, very difficult to map. They're described, but they are not clearly mapped. And they are almost described as if in passing. The security perimeter, site security, is described again briefly, but there's no detail to the kind of what that site security will entail. And I think we can assume that it will be security similar to the levels at the nuclear generating stations, which is armed force. And that details should be reasonably expected to be in, even at this conceptual stage, because it's known at the generating stations, but it again is excluded. The shafts to the underground facilities, there are 3 shafts to the underground facilities, and these all present real areas of risk in terms of releases from the underground facility, releases to surface. Radioactive waste storage areas are identified, are named, but again are not described in detail. Settling and retention ponds are described in brief. And disconcerting detail that is included is that the settling and retention ponds will be released. So the settling and retention ponds will receive both water pumped from underground, but also the liquid radioactive waste, and it will be discharged to a natural water body, potentially after treatment, but it will ultimately be released to a natural water body. And there is no intention to monitor surface water for radionuclides, limited intention to monitor groundwater, no stated intention to monitor surface water, despite the fact that these settling and retention ponds are going to be discharged to surface. And then there's also sealing material and compaction plants as part of the surface facility. So some of the issues with the surface facilities and the used fuel packaging plants, the defective fuel, so fuel that has cracking, hairline fractures, pinholes, some kind of defect, it will be segregated and or repaired. No description or discussion of how a repair could take place, but there's insufficient description of the inspection or the detection to determine which fuel is defective, how the defective fuel would be repaired, or the end strategy for defective fuel that cannot be repaired. Their inspection, detection, and verification processes at all stages are general references, but no description or detail, or insufficient detail to the description. Radioactive waste will be generated at the facility, but again, insufficient detail or description, including the long-term management and isolation. There is a statement that low and intermediate level waste will be shipped off-site for long-term management, but again, insufficient detail. And then there's that issue, very troubling issue around dosimetry devices will be used to measure radiation dose for some employees. Which employees is I think a really central issue. Just a few more issues with the surface facilities and the used fuel packaging plant. There is a stated intention to free release lower level radioactive waste. So free release means to no longer manage it as radioactive waste, but to release it into local landfills, distant, or into the general recycling stream, metal recycling stream. There's mentioned earlier that the liquid waste from the underground sumps and the used fuel packaging plant will go to settling ponds and then release into a local water body. And there's no indicated plan to monitor surface water for radionuclides. The air from the underground facility will be ventilated to surface. So air from deep underground will come 500 meters or more and released through a stack at surface. And the document states that that is for dilution purposes. That's a concern. It's even more concern because there is no HEPA filtration plan for air being pumped from underground during what they call normal operation. So during the day, year after year, decade after decade of operations in the underground facility, there is no intention to filter that air, to use a HEPA filter, which is something that I think most of us would have just assumed would be the case. It is not the case, no intention for filtration. A release event, i.e. an accident or a large release, would trigger then the activation of a HEPA filter. The document includes an estimate that it will take 3 minutes for the air subsurface, the air at depth, to reach the surface. And the NWMO estimates that within that 3 minutes of detecting a large release, that would trigger the filtration, the HEPA filtration, it would go into effect before the 3 minutes pass, and that contaminated air, potentially highly contaminated air, reach the surface. So thank you for that. And now I'm going to turn it over to Bill Knoll with Protect Our Waterways. And Bill is going to give us a summary of lessons learned from the SKB facility in Sweden. Bill.
Thank you, Renee. I will, most of my information is from a presentation, actually originates from the Environmental Impact Statement Report of March 2011, which was authored by SKB. SKB is a similar organization to the NWMO. They are financed by the nuclear industry in Sweden. So I'll look at the first component here, illustrated on this slide, is an interim central storage called CLAB, which is located at one of Sweden's major reactor sites. It was built between 1980 and 1985 and was put into operation in 1985, June 1985. The spent fuel is first stored for some time in pools at the power plants, after which it is interim stored in CLAB awaiting encapsulation. They call it encapsulation instead of repackaging, for the final disposal in a planned DGR. CLAB's underground part consists of 2 parallel rock caverns. They call it CLAB 1, CLAB 2, and they're situated about 30 meters below the ground surface. Each rock cavern contains 5 storage pools in which the spent fuel is stored. The pools in both rock caverns hold a total of 30,000 cubic meters of water, which provides the radiation protection while cooling the fuel. The pools are connected by a 40-meter-long water-filled transport channel. The total permitted capacity at this site is actually 8,000 tons, a lot less than what we have here in Canada. The incoming spent fuel is transferred to a storage container in the pools located at the CLAB's above ground facility, and then lowered by an elevator to the pools below ground. At the time of this report, which is back in 2011, about 5,000 tons of spent fuel from nearly 40 years of operation of the Swedish power plants is stored in CLAB. SKB's plans assume that there will be another 50 to 60 years of operating time for the current reactors, and by that time, the spent fuel is estimated to be at 12,000 tons, which will be contained by 6,000 copper canisters, and I'll talk about those copper canisters a little later. The average storage period in CLAB is about 45 years, so a lot longer than what we're talking about, 10 years in the case of what Bernane said. From the CLAB pools, the plan is to transfer the spent fuel again by elevator to pools in the planned encapsulation facility. The choice of which fuel assemblies are bundled for encapsulation will depend on the decay heat and the permitted heat output in each canister. The decay heat in a fuel assembly depends on the fuel's burnup. In other words, how much energy has been extracted from the fuel and how much time has passed since it was taken out of the reactor. After about 30 years of storage in CAB, a typical fuel has a heat output of about 800 watts per ton, which is comparable to an ordinary electric radiator or powerful toaster. Now, in this case, I have not been able, in all the reports that I've read, to found anywhere in the NWMO reports that talks about when they will allow the fuel to be transferred to a DGR. So this is one place where I find information much more specific in the case of the SBK report. My next slide really describes the planned encapsulation plant. The plant will be erected immediately adjacent to CLAB, and the two facilities will be operated as a single integrated facility, and it's called CLINC. The advantage of locating the encapsulation plant at CLAB is that the personnel's experience of fuel handling can be taken advantage of. And at the same time, SKB can utilize the existing systems and the plant parts in CLAB for the encapsulation plant. The facility will be built with 3 stories below ground and 7 stories above ground. The surface parts of the facility will house the encapsulation process and service the transportation function. So from the incoming fuel from the reactor sites will be dealt with here and transported to the surface part of the pool. A pool selection will be built in the rock, whose bottom will be 15 meters underground. The pool section will be located above the rock cabins that hold the CLAB pools. So they're right up one above another. The spent fuel is transported from the storage pools in CLAB by the existing fuel elevator and placed in the encapsulation plant pools. From there, the nuclear fuel is sorted in the handling pool. This is where the fuel decay heat can be measured to determine if it's safe to place in a copper canister and then ultimately in a DGR. The fuel is then taken out of the pool and put into a handling cell to dry. Up until this point, it's always been wet. So the fuel has never been in any cold storage facility. It's always been in the pools. The fuel is taken out of the pool and put into the handling cell to dry and then placed in a nodular iron insert in the copper canister. When the canister is full, a steel lid is fitted on the insert. A copper lid then is welded into the canister. The insert in the canister is sealed and the air is replaced with inert gas. Now the copper canister in this case is delivered ready-made to the encapsulation plant. It is composed of a cylinder-like container with a shell overpack of copper and pressure-bearing insert of this cast nodular iron. The insert is provided with channels for the placement of the fuel assemblies. The copper canister is about 5 meters long and has a diameter of about 1 meter. The thickness of the copper shell is 5 centimeters as opposed to the 3 millimeters in the case of NWMO. A copper canister filled with 2 tons, so it gets filled with 2 tons of spent nuclear fuel, weighs between 25 and 27 tons. So in addition to the spent fuel, the two tons of that, the main components are 7.5 tons of copper and 14 to 15 tons of iron. So it's a very heavy canister. The encapsulation plant is designed for production capacity of about 200 filled canisters per year, about one canister per week or per workday. The planned production rate is an average of about 150 canisters per year, and the ultimate planned capacity, as I mentioned earlier, is about 6,000 canisters over the expected life of the Swedish reactors. And it will then take approximately 40 years to place all of the spent fuel in a DGR. The plan assumes that releases of radioactive when the encapsulation plant can only occur from the spent fuel to the water in the plant's pools or to the air in the plant's handling cell. All handling of spent fuel takes place in isolated and radiation shielded areas with control ventilation. Different areas are classified based on the risk of contamination and hear my dogs in the background. Sorry about that. And the radiation level. The classification of the so-called control area governs restrictions on access to the area. SBK's assumption is that once the fuel has been encapsulated, it is no longer a source of airborne radioactivity, but radiation shielding is nevertheless required during this further handling. Before the fuel is taken into the encapsulation plant, its radioactive has declined during the interim storage in cloud. This means that the radioactivity that can be released per handled fuel assembly is much less in the encapsulation plant than in CAP. So my next slide talks about the overview of what they call this whole process, a KBS3 method. The applications for license, and this is quite different than Canada, for the encapsulation plant and the final repository are based on a disposal of the spent fuel according to this KBS3 method. The KBS3 method has been under development since 1970. The Swedish, the government, Stipulation Act was passed in 1977 and entailed that no new reactors could be put into operation unless the nuclear power companies could show that the high-level waste could be disposed of in a safe manner. And by the way, this is still ongoing. So even though this report was written in 2011, and it's about a 338-page report, we are now finding ourselves at 2022, and the fact is that the program has not moved that far ahead. In the years around 1980, the Swedish view of reprocessing as the main line of dealing with spent fuel changed. Instead, direct deposit in a DGR was seen as the most reasonable alternative. The KBS project third report in 1983 presented the concept of an encapsulation of the spent nuclear fuel. The method involved, as I already have talked about, encapsulating the spent fuel in copper canisters, which then are deposited, suffered by a buffer of bentonite clay, in holes of a tunnel system at the depth of 500 to 700 meters. The purpose of these 3 barriers, in this case, they've only got 3 barriers. In the case of Canada, it's 5. The canister, buffer, and the rock is to isolate the radionuclides in the fuel from the surrounding environment. Now to my final slide about some of the major differences between the NWMO and the SDK plan. My view, and this is only my view, and it's that there is nothing common in these two approaches other than digging a 500 to 700 meter hole in the ground. Every other major work operation is different. So there's very little learning, in my opinion, from the Swedish that can be transferred to the Canadian situation. The repackaging facility location, as I mentioned, is directly, and in this case, they call it encapsulation, is directly above where the fuel is currently stored. So there's no real problem with training a crew for the operation of the repackaging facility. And you can use a lot of the same capabilities of the CLAB in the encapsulation location. Radioactive releases at the repackaging facility. Sweden does not require the use of hot cells. Or the other aspect that you got going on in Canada is spraying this copper layer at the repackaging facility. Both of those are things that are not used in the case of Sweden. The DGR container obviously has significant differences besides the size of the container. And the Swedish report for the complete system operation is, in my opinion, one of the most comprehensive and provides a lot more detailed information than any report I've read from the NWMO. So the bottom line on this, it's a very, very comprehensive report. It has information about the doses that people will receive or workers will receive in this location. It goes on to explain things such as, how radioactive material or can damage cells through DNA operations. So it's a very comprehensive report, and I found it to be a very interesting read. So that's kind of the overview of what happens in Sweden.
Great. Thank you very much, Bill. That was really helpful. I'm going to really briefly make a couple of observations on the Yucca Mountain project in the US. And many thanks to Steve Freischman from Nevada, who gave me some guidance, pointed me in the direction of some of the materials, and gave me some analysis of where things are at now with Yucca Mountain. So the Yucca Mountain project has been ongoing for decades and has been stalled for, I think, about a decade now. But there's some interesting observations, I think, that we can draw from the Yucca Mountain experience that will inform our assessment of the NWMO project, particularly around this issue around how the waste is handled prior to transport, during transport, and at the hypothetical deep geological repository site. So the current one report I'll point to is a report from 2005 on commercial spent fuel handling in air study. And it made some observations that currently, at that time, the approach was to handle the fuel at transfer at the Yucca Mountain site in air, as compared to, this is air versus in water, as Bill just described in the Swedish process. But they found that the contamination levels, prior to this report, it had been found that the contamination levels and the dose rates from that handling in air, including through hot cells, was higher than acceptable. And it also found that in that handling of the used fuel, there are cladding breaches. So these are things like hairline fractures, pinhole breaches. Those are the kinds of references that the NWMO makes when they describe defective fuel. So cladding breaches are, in effect, it's different language for defective fuel. So in that defective fuel, it had been observed that the uranium, the UO2 fuel would oxidize and generate U3O8 powder, not power, powder, if it was given enough time and at elevated temperature. And then that, through the oxidation process, there could be a fuel could swell, which then puts outward pressure and further degrades the cladding, the container at that point, the remaining barrier between the fuel and the environment. There was a statement made in the following year, I think, that summarized this in a statement by to the Standing Committee on Energy and Natural Resources, summarizing analysis of the use of hot cells handling in air at the Yucca Mountain. And that analysis indicated that there could be severe radionuclide contamination and worker safety problems, and that attempts to resolve those issues had not been satisfactory. And so that they were instead moving to a plan that commercial spent fuel would be loaded into canisters and welded closed at the reactor. So there would not be, that would then eliminate this need for a transfer at the Deep Geological Repository site. In that case, they were talking hypothetically or in a proposal about Yucca Mountain, just as the NWMO is talking hypothetically about a site in southwestern Ontario or northwestern Ontario. The current waste handling plan or intent for Yucca Mountain is to have it come in already in the transportation. It moved into transportation casks, which are then direct disposal into the underground facility, or for those wastes which would arrive and would not be already in a direct disposal container, it would be handled in water in a wet pool at the site of the Deep Geological Repository. Of course, we don't know that Yucca Mountain has any future. We don't know what future attempts might be in the US for the siting of a Deep Geological Repository. But I think it's a fair summary to say that in the Department of Energy thinking, in the sort of the waste track in the US more generally, there is no longer an expectation that the waste would arrive at the DGR site and be repackaged through the use of hot cells, or what they call air handled at that site. And that is because both of worker contamination and release of contaminants, but also these issues around further degradation of the fuel. Some additional insights from Yucca Mountain, and this is from that last report that I displayed. It identified that radiological impacts to workers, which are estimated in cancer deaths, and certainly cancer death is not the only health consequence of an exposure to radiation, but those were estimated at 7 to 12 chances in 1,000. And it was estimated that 70% of those radiological impacts to workers would occur during the operations period, and the larger contribution would be surface facility operations. The second largest contribution would be worker impacts carrying out subsurface monitoring, and that would increase proportionally with the length of time of monitoring. Now, we can't directly extrapolate from this. It's a very different project, different design and so on, but I think they are insights or observations that must have bearing on the way we review and consider what the NWMO is or may at some point propose for the transfer of the high-level waste if they continue to propose that transfer take place at the site of a Deep Geological Repository. And I'll just note that those estimates above are based on direct or pool transfer, not using the hot cells. So I think we can expect that if we saw similar estimates using the hot cells, those numbers would be even higher, at least in terms of the estimates of cancer death. So thank you for that. And now I'm going to turn it over to Ole Hendrickson from Concerned Citizens of Renfrew County and Area. And Ole is going to describe for us some of the experience with hot cells at the Chalk River nuclear laboratories. All.
Thanks, Brenane. Our group, located in Renfrew County, is very close to the Chalk River laboratories, and this is not my area of expertise. There may be some people on this webinar who are much more knowledgeable than I, but this has been a good learning experience for me. So next slide, please, Brenane. I think last week's webinar, Gordon showed a picture of a hot cell at the Argonne National Labs in the United States. And this is another picture from Argonne. I couldn't find a good one from Chalk River. And you can see the remote handling of the highly radioactive fuel inside that shielded hot cell through the window. Next, please. So this is not a hot cell facility, but this is what's known as the recycle fuel fabrication lab at Chalk River, where they have equipment for manufacturing what are called mixed oxide or MOX fuels from plutonium, uranium, and thorium. And these are glove boxes and fume hoods, which are required so that airborne alpha particle emitters such as plutonium, uranium, thorium do not contaminate the environment and the workers. And I'll come back to glove boxes later. So I just wanted to show a quick picture of that. Back one for name. This is one of the hot cell facilities at Chalk River. You can see it's a fairly old building. This is the fuel material hot cells where they do fuel analysis. They cut up fuel rods, they polish, they do metallography, they measure radiation with gamma spectrometers. They look at the burn up, how hot and radioactive fuel gets after different periods in a reactor. And they do few element leak testing. And of course, as we've already discussed in this webinar, fuels can develop fractures and cracks and release some of the contents. Next. And this is the other hot cell facility currently at Chalk River, where they receive fuels from other facilities for testing. This is where repackaging gets done at Chalk River. So maybe this is somewhat similar to what you might see as a repackaging facility at the DGR site. They do various other activities such as what is called pressure tube burst tests. And I'll come back to that one later in the presentation. So those are the two hot cell facilities currently at Chalk River. Next is the proposed brand new Advanced Nuclear Materials Research Center. And this would be an artist rendition of a $1.2 billion facility that would include 12 new shielded hot cells. And the aim of this facility is mostly supposedly to enable testing and post-irradiation examination of fuels from small modular reactors, as well as the glove box facilities that we saw earlier, in which they could fabricate various types of fuels. So since we don't have any small modular reactors in Canada, it does kind of beg the question, well, where are they going to get the SMR fuels to irradiate and test? But this is this is the largest new capital project at Chalk River, which in turn is Canada's largest federally owned research and development facility in the whole country. It's a very large facility. There are well over 2,000 people working at Chalk River. Now, this facility, although there has been an announcement of signing of a project agreement to build it, we have yet to see any sort of license application or initiation of a assessment under the Federal Impact Assessment Act. Next. Okay, I want to talk a bit more about SMRs. This is another pretty picture of a facility that is an artist rendition of a 300 megawatt electrical reactor that's proposed by Moltex Energy. And the reason I'm showing this partly is because Canadian Nuclear Laboratories, which is headquartered at Chalk River, has a partnership agreement with Moltex and the University of New Brunswick to build a fuel testing apparatus for Moltex. Now, the initial fuel testing apparatus would use surrogate inactive materials, but then Canadian Nuclear Laboratories would move that apparatus into a hot cell. And that's where testing could be completed using actual irradiated fuels. So we don't know whether this shielded facility would actually be constructed in New Brunswick or perhaps in Chalk River. And I also mentioned Jacobs Engineering Group, which is part of this as well, at least part of the reactor construction. And remember, that's a picture of the reactor, not a picture of the hot cells or fuel testing apparatus. And Jacobs is one of the three owners of Canadian Nuclear Laboratories. It's part of a three-member consortium of two Texas-based groups. That's Jacobs and Fluor, and Canada's SNC-Lavalin. They're part of a consortium that has been hired on contract to operate all the federal nuclear facilities around Canada, and most of that activity takes place at Chalk River, and they own Canadian Nuclear Laboratories. Next. So this came up last week. And I really found this interesting because you'll recall that Frank von Hippel and Gordon Edwards and MV Ramana were talking about thorium, and that was in response to a question I asked. So I did a little bit of research on thorium fueled nuclear reactors and learned that China is actually planning to test one, or maybe already testing it. This is not a picture of China's thorium fueled reactor. This is another one of China's nuclear reactors. And as was mentioned last week, thorium has nuclear weapons proliferation risks, because if you leave thorium irradiated in a reactor for a fairly short period of time, you can extract fairly pure uranium-233, which is it's very easy to make nuclear weapons from U-233. So in order to do that, you need to extract protactinium from the irradiated thorium, and that requires a hot cell. So hot cells are considered by the International Atomic Energy Agency to be significance for weapons proliferation. And Canada and many other countries have signed an additional protocol to the Non-Proliferation Treaty. And any new hot cell facilities have to be formally disclosed by Canada and other parties to this protocol. And as far as I know, they haven't yet disclosed the new hot cell facilities for Chalk River, but presumably that will have to happen if Canada wants to remain in compliance with the Non-Proliferation Treaty. Next. I wanted to come back to the pressure tube burst test. I got this from an old AECL publication about the kinds of work that is done in the hot cell facilities at Chalk River. So as many of you will know, as you leave fuel in a nuclear reactor and it becomes irradiated, fission gases build up and in the fuel, and they sort of form little bubbles, and the fuel can swell. And the longer you leave the fuel in, and that's what an extended burnup means, then the fuel gets hotter and it gets more radioactive, and you can get stress corrosion cracking because the pressure builds up in the fuel bundles, and that high gas pressure can reduce the thermal cooling of the fuels and can create higher fuel temperatures. So a lot of these tests, particularly of higher burnup fuels, have been done at Chalk River just to see how long you can leave a fuel rod in a reactor before it gets too hot, too radioactive, and the cladding starts to deteriorate. So at Chalk River, we have a lot of these sort of experimentally tested fuels that may have been punctured for a pressure tube test, and those, to my knowledge, are not going to the DGR. Those are now in what they call tile holes at Chalk River, buried in the ground at Waste Management Area B. We don't have any plan for what to do with them. And there's quite a bit of this experimentally tested fuel. Some have been sawed in half and they've been punctured and so forth. So this is a part of the high level waste inventory in Canada that we don't tend to talk a lot about, and that, as far as I know, the Nuclear Waste Management Organization isn't going to deal with. Next, please, Bernane. So, and I wanted to just throw one more slide in about this possibility that there will be radioactive gas releases during the repackaging operations, because, as we say, whether they're cracks or fractures in the irradiated fuel elements will determine whether some of the fission gases and carbon-14 can escape from the fuel. So I'm repeating myself a bit, but during reactor operations, the gases increase pressure and temperature, both in the fuel and in the gap between the fuel and cladding. And we also know that the alpha particles that are being constantly given off by the uranium and plutonium and other actinides, alpha particles are helium, and helium is gas. So that also creates increased pressure and gas buildup in the fuel elements. But they're not just helium, but they're also radioactive fission gases. And particularly iodine-129 has a very, very long half-life, and it has a fairly high fission yield. Nearly 1% of the fission products in the fuel are iodine-129, and krypton-85 is another major fission product with a fairly long half-life. So the possibility is, if you have cracks or fissures in the fuel elements, that those gases can be released, as well as radioactive carbon-14, very long-lived, which is also generated inside nuclear fuels. But it's not a fission product, but it's a sort of transmutation by neutron activation of nitrogen and oxygen in the uranium oxide. So that's pretty well what I've had to say, Bernane, just a little bit about where those radioactive gases may come from in a repackaging operation.
Great.
Thanks.
Thank you very much, all. That was really, really helpful. And I think part of the information that I think we really need to understand what's going to happen at this theoretical facility, and it's information that isn't provided in the NWMO documents to date. Just in summary, the surface facilities, and particularly the used fuel packaging plant, is what we've looked at tonight. They're really at a concept level of design. They may change significantly. And this happens in the context of the NWMO expecting a community to be informed and willing and make a declaration of their willingness by 2023, when we have these very significant parts of their project still without adequate levels of description, detail that would really allow the communities, the regions, to be able to determine how acceptable or unacceptable this project is. In what we've seen to date from the NWMO around the used fuel packaging plant, as with the deep geological repository, but we're focused on the used fuel packaging plant this evening, there's really limited information about the radioactive releases and the waste that will be generated, how they'll do the monitoring, how they'll do the filtering. And experience elsewhere shows us that there is evidence of contamination from the current approach that the NWMO is suggesting of fuel transfer, i.e. Moving the fuel to the intended geological repository and doing an in-air transfer at that site. And the design to date shows limited commitment to environmental or personal monitoring or to minimizing releases of radionuclides to air and water. So that, I think, you've been very patient. We are over our time. I'm going to turn off the recording and we'll go to question and answers. So thank you very much, Ole and Bill, for those really excellent presentations.